All right, sorry about that. So let me just do a quick recap of what we were talking about. So we were asked to find the limit as x goes to infinity of 6x squared plus 100 divided by 7x squared minus 100. We used this trick where we took the variable with the highest exponent on the denominator and we multiplied the numerator and denominator by the reciprocal of that. In this case, it was 1 over x squared. That's the reciprocal of x squared. And then we simplified a little bit. So we had the limit as x goes to infinity of 6 plus 100 over x squared and divided by 7 minus 100 over x squared. And what I was saying is that as the numerator, when the numerator stays the same but the denominator grows, the fraction as a whole becomes smaller. So you could see it with, you know, something like 2 over 3, which is roughly 0.67. 2 over 4 is 1 half. 2 over 5 is definitely smaller than 1 half. It's 0.40. And 2 over 6 is 1/3, so that's 0.33. So you can see that the fraction is getting smaller from 0.67 to 1 half, 0.40, 0.50. So I mean, it's right better. Anyway, so as we take the limit, the 6 and the 7 have nothing to do with x, so they stay the same. But 100 over x squared, that limit is going to 0. So what I'm doing is I'm doing the limit now. So I pull out the 6 over 7. And I'm doing really the limit as 100 over x squared goes to infinity divided by minus 100 over x squared goes to infinity. And this piece is going to be equal to 0. So this piece is equal to 0. So we just get 6 over 7 as our limit. Now, back when we did this problem, I told you that this problem really comes from an idea from pre-calculus with the horizontal asymptotes. So now, if you remember from pre-calc, when a function has a horizontal asymptote, three things could be true. The degree of the numerator could be bigger than the denominator, the degrees could be equal, and the degree of the denominator could be bigger than the numerator. Here, the degree of the denominator is 2, and the degree of the numerator is also 2. So this has degree 2, this has degree 2, which means that the degrees are equal. That means that the horizontal asymptote of this expression is just the ratio of leading coefficients, which is 6 over 7. So right off the bat, we could have said that the limit was going to be 6 over 7 because that's the horizontal asymptote. When you draw that graph, I don't care how it looks at this point. I know that this graph, as it goes to infinity, cannot cross the horizontal line 6 over 7. Let's say it's somewhere up here, 6 over 7. So it cannot cross this horizontal line ever. So if the function looks like this or like this, it's not going to cross it as it goes to infinity. Okay, so that's by using the fact of horizontal asymptotes. Had the denominator been bigger, then we know that the horizontal asymptote is just 0 because of this fact. Okay, so that's something that you should definitely keep in mind. That is something that you should definitely know. Okay, so let's move on with question number 9. I was gonna pause and break this into 2 pieces, but I guess now because of the issue of the pan, it's broken into 2 pieces. So I probably will go straight through up to question 20. Now, question number 9 is an interesting one. It has to do with continuity. And that's the following: for each constant k is the following function q of x continuous for all x. Now the function given is q of x is a piecewise function that is x squared plus k when x is less than or equal to 0, and is cosine of x whenever x is bigger than 0. Okay, so what do we have here? Well, we have two functions. We have cosine of x and we have x squared. Now, there are many ways of doing this problem. One of the ways that you could do it is to equate the functions. You could do something like this and then figure out what the value of k must be by plugging in x. So that's one way of doing it. So we have 0 for x, just because x could be 0 on the top one. Now, I'm going to plug in 0 for both of them, even though cosine of x has to be strictly bigger than 0. But I'm going to plug it into both of them and see what I get. So we have 0 squared, because I see that the issue may be around 0, because that's where the function breaks. Okay, that's where they become different. So I'll just plug in for both of them and see what's actually happening there. So I have 0 squared plus k is equal to cosine of 0. 0 squared is just 0, so that's 0 plus k. Cosine of 0 is 1. So if you remember the cosine wave, it looks like this. It goes from 0 to 2 pi, but at 0 is equal to 1. So we got 0 plus k, that's just k, so k must be equal to 1. So for this function to be continuous for all x values, k must be equal to 1. Now, let me show you what's actually happening here visually. Cosine of x looks kind of like this. Right. We're only interested in cosine values that are bigger than 0. So we're only interested in cosine being on the right side. X squared is a parabola, and it looks like this. Right? Now, if I were to do the following, there's too much. If I were to do the following, and instead of drawing it like I had it before, I draw it like what the piecewise says, it will kind of look like this. Because the function is supposed to be x squared when x is less than or equal to 0, and it's supposed to be cosine when the function is bigger than 0. So there's an open hole at 1 for cosine. If I want this function to be continuous, then two things need to happen. Either the cosine function comes down or the x squared function comes up. Well, the k value that we are concerned about is with the x squared. So that means that we have to bring up the x squared function up with a vertical shift. And notice that to bring it up to 1, I just simply need to add 1 to x squared, because if you remember, whenever you add a value, we just shift the parabola up or down. So if you add, you shift it up. If you subtract, you shift it down. So if you added 3, it will look like this. If you subtracted 3, it will begin at -3. That's all. So here you have two ways of doing it. You could graph it, and then you could make the determination of what the shift should be, or you could equate them and see what happens at the that point and solve for k. Okay, so that's two ways of doing this problem. I like the graphing method, but both methods work. And I do suggest that if you go for this method of equating and then plugging in at that point, that you still draw the graph just to make sure that what you drew makes sense. Okay, so that's problem number 9. It's a neat problem. I mean, it involves continuity. You can also take the limit. So another way of doing this problem is to take in the limit from the right side and the left side of the problem. So if you took the right side limit for cosine, you get that limit is 1. If you took the left side limit for x squared, you could have seen that limit is equal to 0. And for them to be the same, the left side limit of x squared must be equal to 1, and that's also a giveaway of what you need to k to be. K needs to be 1 for that to be true. Okay, for them to be continuous. All right, so that was number 9. Problem number 10 is to show that the following derivative is actually equal to what we're saying it is. So show that the derivative f of x equals 1 over x is 1 over x squared, negative 1 over x squared, by using the limit definition of the derivative. Definition of the derivative. The question is actually worded a little bit different. The question is worded as the limit of a quotient of difference quotient, but that's the limit definition of the derivative. So if you don't recall, when we define the derivative, we define it as a limit, and it's the limit of as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. Now, because of the delta x, I'm just going to use h as delta x. I'm not going to use delta x. That's the way that we defined it way back when. So what we have here, we have f of x is equal to 1 over x, and we want to show that f prime of x is equal to negative 1 over x squared by using this definition. So we basically just need to solve the derivative and make sure that what we get as a solution is this. So we know what the solution should be. Okay, so let's start. So we have limit as h goes to 0 of f of x plus h. I'm using h instead of delta x. So that is 1 over, remember, I'm going to plug in for x the inside piece, or the input, which in this case is x plus h. So it's going to be 1 over x plus h, because my function is 1 over x, minus the actual function, 1 over x, divided by h. Okay, so here I have a complex fraction, and what I will choose to do is to first combine the fractions in the numerator and then multiply the reciprocal of h. I could also use the GCD. I could find the GCD of the fraction and then multiply through by it, but I don't like doing that. But you could do it. So I just multiply by what's missing. So on this fraction on the left side, what's missing is an x over x, and on this one we're missing an x plus h over x plus h. Okay, so what we will have is x over x times x plus h minus then multiply 1. So I'll simply just distribute everything through. So I'll just distribute the negative 1 into it. So then minus x minus h over x times x plus h divided by h. Now that the denominators are equal, I will combine the fractions. So again, this is the limit as h equals to 0 of x minus h divided by x times x plus h, all divided by h. And the x's in the top, notice that they'll cancel out. So I'm going to have limit as h goes to infinity, to 0, not infinity, of negative h divided by x times x plus h, all divided by h. Now, because it's a complex fraction, instead of dividing by h, I'm going to multiply by its reciprocal, which is 1 over h. So what that means is I'm going to do limit as h goes to 0 of negative h over x times x plus h times the reciprocal of h, which is 1 over h, of this h. That h became this. Now, so long as h is not 0, we can cancel the 1 in the numerator with the denominator 1. So we have limit as h limit as h goes to 0 of negative 1 over x squared, I'm just going to multiply through now, plus xh. You distribute the x's here. And finally, we can simply use the plug-in method to take the limit. So the limit of -1 over x squared plus x times h is simply -1 over x squared, because you plug it in 0 for h, and 0 times x is 0. So we do have, in fact, that f prime of x, which is what we wanted to find. So this is f prime of x is equal to -1 over h, -1 over x squared, which is exactly what we got down here. Now, for the exam on my lab, unless it asks you to show your work, you probably will have just a multiple choice answer, unless it asks you that in person. If you have the exam in person, then you will have to show all of this work. Okay. All right, so that's using the limit definition of the derivative to solve the particular problem. All right, so now we get into the more interesting problems. So this particular problem asked us that if the volume, this is more for later rates and applications of the derivative, if the volume V equals s cubed of an expanding cube, is increasing at the constant rate of 120 cubic inches per second, how fast is the length s of the size increasing when the volume is 8 cubic inches. Volume is 8 cubic inches. So now we're given a formula for the volume of this expanding cube. That is, V is equal s cubed. We are told that the cube is expanding and it is increasing, meaning the volume is increasing at a rate, so that means dV dt, the rate of change of the volume with respect to time, is increasing at a rate of 120 cubic inches per second. Okay, we are told to ask how fast the length s, so the sdt, is increasing when the volume V is 8 cubic inches. Okay, so notice that I have the VDT, I have the SDT, which is what I'm looking for. I'm giving the volume at 8 inches. I don't have the actual length of the sides of the cube. So before I begin to take derivatives, let's actually find out what the length of the side of the cube is. Remember, a cube has equal sides. Okay? So let's figure out what this length sides S are. I am given enough information to find it because I'm told that the volume is, I want to find this information when the volume is 8 cubic inches. So that means that this V up here is 8. And I can solve for S now, for S cubed, by just taking the cubic root on both sides. So if you take the cubic root on both sides, we get that 2 is equal to S. So the length of each side is 2, because 2 times 2 times 2 is 8. So now I have what S is equal to. Now I have enough information to actually begin to use the derivative to find out what the rate of change of the sides is going to be equal to. Remember, to do this, we take the derivative with respect to time for each variable that we differentiate. So For example, the derivative of v is going to be dv dt. The derivative of s cubed is going to be 3s squared times ds dt. So this is something that we did before. Remember, this all comes from the chain rule. So now we have enough information to actually solve for ds dt. ds dt is what we're solving for. We're going to find out what this is equal to. We have information about s, and we know what dv dt is equal to. dv dt is 120 inches cubed per second. And s is 2. So what do we have here? We have 120, which is what dv dt is equal to 3 times 2 squared times what we are looking for, which is ds dt. Now, last time I checked, 2 squared is 4. So we have 3 times 4 times ds dt. 3 times 4 is 12, so we have 12 times ds dt is equal to 120. And hopefully you can see that when we divide both sides now by 12, we're going to get that ds dt is going to be equal to 10. And that is the solution to the problem. Okay? Now, you should always add the units. If we're doing this in person, you should definitely add what the units are, which in this case again is, let me see, we're dealing with inch cube per second. So this is gonna be, and we're dealing with this side, so this is gonna be inch cubes per second. So you should always add those in. So make sure that when you do a problem with related rate, you first, most importantly, just write down all information that's given and find out any possible information that you don't have. Like we had to find what this s was equal to. So you want to have information about every single variable, with the exception, obviously, of the one that you're trying to solve for. So that's how you should attack this related rate problems. You definitely will have at least one in the final. That's for sure. Okay. Question number 12. For question number 12, we have to find where the graph of y equals x cubed minus 6x squared is concave up and concave down, and find all of the inflection points. This is not that terrible of a problem. Remember that the inflection points are given by when the second derivative is equal to 0. And concavity, we use the second derivative at the critical values to find out whether the concavity is up or down. So the first thing we should do is just take the derivative. If we take the derivative, we get 3x squared minus 12. And if we take the second derivative, we get 6x. Now, to find the critical values, which we need, we solve for when the first derivative is equal to 0. So that means when 3x squared minus 12 is equal to 0. So notice we could factor out a 3 here. So this is 3 times x squared minus 4 is equal to 0. And then this becomes the difference of two perfect squares, because 2 times 2 is 4. So this is 3 times x minus 2 times x plus 4. Plus 2, not 4, my apologies. It's equal to 0. So we can see here that x is either plus or minus 2. So these are our two solutions for this. So now we simply have to test this critical values at the second derivative. But let's find the inflection point. So the inflection point happens when the second derivative is equal to 0. Well, when is 6x equal to 0? Well, when x is equal to 0, because if you divide both sides by 6, you just get 0. In fact, if you just plug in 0 for x, you could see it. Let me clean this up a little bit. So 6x equal to 0 when x is equal to 0. So that means that the inflection point occurs at x equals 0. You could actually find out what that point is by going into the original problem and plugging in 0. So the point is, so the inflection point is 0, 0, the origin. Now, to find whether the function is concave up or down, we take the second derivative, which is equal to this 6x, and we plug in the critical value. So we have one critical value, which is -2, and the other one, which is 2. If we plug in -2, we have 6 times -2 is -12. And remember, when the second derivative is negative, we have that this is concave up. Well, no, my apologies, concave down. Concave down, which means we have a maximum. So it's concave down, but we have a maximum. And when the second derivative is positive, we have concave up, which will give us a minimum. So 6 times 2 is going to be equal to 12. It's going to be concave up, but we're going to have a minimum. It's easy to get confused with this, so be careful. I always keep this picture in the back of my head. This right here and this right here. Okay, concave up when the second derivative is positive, concave down when the second derivative is negative, and then it tells you information about when you have a minimum or a maximum. Speaking of minimum and maximum, the next problem talks about relative extrema. So problem number 13 is the following. It's to find and classify all relative extrema of f of x is equal to x to the 4. And my problem, well, there's no sign here, so I'm going to go with a positive, and hopefully this works. X to the 4 plus 4x squared plus 2. Hopefully it's a positive and not a negative there. Okay, so let's see what happens here. Just think a little bit about this. Okay, so let's see what happens. So let's take the derivative. We're going to get 4x cubed plus 8x, and that will be it because the last one is just 0. I think this is fine. Yeah, I think this is fine. So to find the critical values, again, we have to find out where the first derivative is equal to 0. But before we do that, let's just simplify this a little bit. I could pull out a 4x from both of them, so I'm left with x squared plus 2, and definitely should have been a negative, because if it's a negative, then the problem becomes easier. So I'll make this a negative. I believe it should have been a negative. I mean, it works with the positive too, but it's gonna be more challenging to actually solve the middle portion because we're gonna be dealing with a complex number here if this becomes a positive. Anyway, we now have to solve for this. So let's see what we get. We get we have to solve for when 4x is equal to 0 and for x squared minus 2 is equal to 0. So 4x is equal to 0 when x is equal to 0, and x squared is equal to 0 when x is equal to, so plus or minus radical 2. Okay, so now we have our critical values. These are our critical values. They are x equals 0, minus radical 2, and radical 2. Now, because we have to classify the relative extrema, what this means is to figure out where the function is increasing and decreasing. So again, one way to do it is to use the second derivative test, but we could also use the first derivative test. Either one is fine. I'm gonna honestly start with the first derivative test and see how that goes. So the derivative is f prime is equal to 4x times x squared minus 2. And now we just need to find values in between these points. We need to find values between 0 and radical 2, between 0 and negative radical 2, and to the left and right of those. So I know for a fact that the square root of 2 is bigger than 1, but it's definitely less than 2. So these are my test values, the negative 2, negative 1, 1, and 2. So now I could just simply plug in by using the first derivative test into all of these, for all of these. So I'm going to have 4 for f prime of 1, meaning for this test value, I'm going to have 4 times 1 times 1 squared minus 2. That's going to be equal to 4 times negative 1, which is negative 4. Remember, when the derivative is negative, that means that we're decreasing, so we're going down. And let's see f prime of 2. We have 4 times 2 times 2 squared minus 2, so that's going to be a positive number because it's going to be 8 times 2, which is going to be 16. So it's going to be increasing. So here we have concave up. So you're going down from 0 to radical 2 and then up to the right side of that. So we have a minimum. We have a local minimum at radical 2. And on the other side, if we use negative 1, we have 4 times negative 1 times negative 1 squared minus 2. That's going to be negative 4 times negative 1, which is going to be equal to 4. So that means from radical from negative radical 2 to 0, we're going to go up. And finally, at negative 2, we have f prime of minus 2, which is equal to 4. So it's minus 2, minus 2 squared minus 2. So it's going to be negative 8. And then on here, we have 4 minus 2, so it's going to be negative 2 again. Actually, no, that's plus 2. It's 4 minus 2 is 2. So plus 2, so it's going to be negative 16. So this is going down. So notice here we have another min, and here we have a max. So we can now talk about the intervals. So from minus infinity to negative radical 2, we are decreasing, meaning from this side up to here we are decreasing. From negative radical 2 to 0, we are increasing. Then from 0 to radical 2, we are decreasing again. And from radical 2 to infinity, we are increasing again. Okay, so we now have been able to talk about all of the intervals of the function, and we know where the minimum and maximum occurs. The minimum occurs at radical 2 and negative radical 2, and the maximum occurs at 0. And so let's write that down. Minimums at plus or minus radical 2, and maximum at 0. Okay, so that's the solution to our problem. We have found all of the information about the extrema of the function, and we have found where we are increasing or decreasing. Now these were the local max and mins that we found. This function is not defined on an interval, so we cannot find the absolute max and mins. The next problem, we're actually going to do that. We're actually going to figure out what the absolute max and the absolute min are. So we're asked to find the absolute max and min of f of x is equal to 4x cubed minus 3x squared on the closed interval -1 to 1. Okay, so remember when we find absolute max and min, we have to evaluate the function at the endpoint and at any of the critical values that happen to be in the domain or in the interval given. So what I will do is first I'll just simply take the derivative. So f prime of x is equal to 12x squared minus 6x by the power rule. And then we will figure out when is f prime of x equal to 0 to find the critical values. So that is 12, when is 12x squared minus 6x equal to 0? Then we will factor out a 6x from here. So we have 6x times 2x minus 1 equal to 0. So we have that 6x is equal to 0 when x is equal to 0, and we have that 2x minus 1 is equal to 0 when x is equal to 1/2. You move the 1 over and then divide by 2, so we get 1/2. So these are our critical values. Notice that both of them lie inside of the domain. 0 is inside of the domain because the interval is -1 to 1, and 1/2 is definitely there because it's in between 0 and 1. So we have to figure out now the value of all 4 of these points on our f of x function, or on our original function. The original function is 4x cubed minus 3x squared. So I'll start with from lowest to highest. So I'll go from f of -1, which is going to be 4 times minus 1 cubed times minus 3 times minus 1 squared. Well, this is equal to, just do it all in one line. This is equal to -4 minus 3, which is equal to -7. F of 0, which is the next lowest point, because it's one of our critical values, is going to be equal to 4 times 0 cubed minus 3 times 0 squared, which is going to be equal to 0. F of 1/2 is going to be 4 times 1 over 2 cubed minus 3 times 1 over 2 squared. This is going to be equal to 4 times 1 over 8. 4 times 1 over 8 minus 3 over 4. And then 4 over 8 is 1/2 minus 3 over 4. But notice that this is just the same thing as 2 over 4 minus 3 over 4, which is equal to -1 over 4. You multiply the first fraction by 2 times 2. So we get -1 over 4. And finally, f of 1, the right end point, is 4 times 1 cubed minus 3 times 1 squared. And that is equal to 4 minus 3, which is equal to 1. Now here we have to find the lowest point and the highest point, because we have to find the absolute minimum and the absolute maximum. Clearly the absolute maximum is 1 because it's the highest point. Everything else is negative. Or 0. But 1 is bigger than 0, so 1 takes precedence. And the lowest value is -7. Okay, so the lowest value happened to be -7. Unless I did something wrong. Let me just make sure. Yeah, no, that's -7. And then this is definitely -1/4. Yeah. Okay, so the absolute max occurs at x equals 1, and the absolute min occurs at x equals -1. Sometimes that happens. Sometimes you'll have the critical values with the lowest point, but in this case it wasn't. So again, that's how you find the absolute max and min on an interval. You evaluate you find the derivative, you find the critical values. After you find the critical values, you evaluate the critical values on the original function, and you evaluate the endpoints at the original function. Not in the derivative, but in the original function. Okay? Let me pause this video here, and we'll pick it up on the third part of this review.